I'd like to introduce Thomas.weible, who will be presenting Coherent Optical Transceivers, Current Capabilities, and Future Possibilities. Thomas is the CTO of Flexoptix, and he is coming to us today from Darmstadt, Hessen, Germany. This is Thomas's first time presenting here at NANOG, and it's a pleasure to have him here speaking with us today. Welcome, Thomas. Thank you so much.
Steve, actually it's not the first time. I had been at NANOG 78 something in Denver. So yeah, this is Thomas.weible from Germany. The Coherent Optical Transceiver talk is mainly a tremendous change in optical transmission actually. Coherent technology is around for a while, but within pluggable transceivers it's quite new, and it came up with 400 gig and beyond. So until 400 gig, like 40 gig or 10 gig or even 100 gig, the modulation was quite simple. Let's say it's simple. It wasn't on-off keying. And I'm gonna move to the next slide, which you can see here on the left top corner. It's a perfect rectangle shape from the 1 down to the 0. And yeah, this was also called the direct detection transceivers up to 100 gig, early stages, 100 gig transceivers. And I split up this talk in two sections. The first one is a little bit about theory, about coherent technology. And then later on, I show you some practical examples, how it's going to be implemented in the field and how you can troubleshoot your network when you run a coherent transceiver or a network based on coherent technology. So as I said, top left corner, perfect rectangle shape. And actually, when you look on the line itself, on a high-speed signal, it doesn't look like this shape. It's more like the sinus wave on the bottom. Now, the challenge with higher speeds coming from 10 gig or 40 gig, we can increase the frequency, that's for sure. So this is like in the middle section. We make it more dense. We squeeze in more bits in the same time slots, but there is a limit, and the more we go to the right or over there as well, and you see in the bottom the sinus wave is getting smaller and smaller, so it's very hard for the receiver to detect a proper 0 and a 1, and that's a big challenge about direct detection. And light has more properties. It's not only the frequency, and that's what I want to talk now about. So the next one, or the first one you are familiar is polarization. Polarization, quite a lot of you are familiar with it. You have a privacy shield on your laptop, and that's actually a polarized filter. And we can use that also for optical transceivers. And typically we use two polarization directions, like 0 degrees and like this, 0 degrees and 90 degrees. And to give you a better example, I have a small animation. So as what you can see here on the polarized signal on the X and Y plane is, and it already changed now, so from the first stage from the X plane to the Y plane, this is a transmitted signal. And so that's the first one again. Dino, can you go to the second one, please? And that's the Y plane. And now when we combine them, that's our actual transmitted signal on the fiber. So it's a three-dimensional structure, basically. And the challenge there is the receiver needs to detect and figure out the zeros and ones out of this. It's not that easy, to be honest. Even as human. So polarization is one thing where we can increase bandwidth with the light, and there are two other factors, is the amplitude, the increase of the light, of the power level, and our phase. So what you see here now is a 16 QAM, and the QAM stands for quadrature amplitude modulation. So we have those 16 dots from the top left and down to the so 4 of each in each section for this matrix. And this is in mathematics in this constellation diagram. And for simplification, this is just one polarization, so we have 2. We have complex numbers to identify it, and there is an in-phase component, the real part, which is on the horizontal line, and on the vertical one is the imaginary part. Yeah. As a reference for you guys, I put also the NRZ signal, the on-off keying, which are the stars. These are 2 of them on the left and right, and they don't have the imaginary part, so only the real part if you would put them into a constellation diagram. And for 100 gig transceivers, PAM4 was introduced, a 4-level modulation scheme based on the amplitude only, and these are the 4 rectangles in the middle line. But as I said, NRZ and PAM4 don't have the imaginary part. A different view on that is when you take that constellation diagram and slice it a little bit, you see we have 3 different types of amplitude. So it's the same constellation diagram, just a different view on it. We have an amplitude, and I do it relatively with 33%, 75%, or even the outer ring is having 100%. And then we have the phase, so we have in total 360 degrees. And as you can see, each dot of which is our symbol has a different phase. And the combination of the amplitude and the phase gives the receiver the possibility to detect the bits at the end of the day. So the symbol right here is 4 bits, so we can encode 4 bits now, which is a major improvement compared to on-off keying, where we only were capable to encode 1 bit. And the other thing here I want to mention is about the signal-to-noise ratio, because that's an important thing for coherent transmission as well. I'm pretty sure some of you are familiar with it. What is the signal-to-noise ratio? It's the difference between our actual signal in relation to the noise level we get on the line, and it's measured in decibel, logarithmic scale, and you can do this typically for the optical light level. You can also do it on the electrical side. Both you are able to measure. And why is this important? When we go back now to our constellation diagram, we plotted now 3 different SNR values. So on the left side, you see a constellation diagram with an SNR of 30 dB. It looks perfectly. It's a nice matrix. You can identify the dots pretty well. The receiver can do the same. It can really identify each symbol. We have 16 of them. And when we decrease the signal-to-noise ratio, so it's getting weaker, the signal, you see it's a little bit blurring, like in the middle one. And when it's only 5 dB, it's actually not detectable any longer. So there are a lot of errors now. The receiver can't detect the proper symbol any longer. It looks like slurry at the end of the day. It's like, yeah, not usable. Right. So this is so far the theory part about the coherent. There are some other factors for coherent transmission as well, but I think for this scenario, which I want to show now, these are the important ones. What we did is, together with DKIX in Germany, they are running quite a huge installation with Nokia SR routers, and so we used the 400 gig SATA transceiver in their Nokia gear, and we basically just looked with one command, show port command, what do we get back from the router, and what is the important information we use there. And yes, show port shows us pretty much the capabilities at the first section of this transceiver. It's a fully tunable coherent transceiver. You see the start and stop frequency starting at 191.3 gigahertz up to 96.1 gigahertz. So at the end of the day, channel 13 up to channel 61. It can support different grids, 100 gigahertz or well-known 50 gigahertz and some slices between there as well. And currently it's tuned to channel 23. You see this here at the operation frequency. It's shown in megahertz, but it's channel 23 then. The second one is digital diagnostic monitoring. I'm pretty sure everyone is familiar with digital diagnostic monitoring so far, and if not, please get familiar with it, because it's very helpful to get the actual live values out of the optical components, on which voltage are they running, and what are the power levels, the receive and transmit levels. I've highlighted now the temperature here because for coherent transceivers, the temperature is a critical thing. They draw out up to 17 watts out of a QSFP-DD port, and that's quite a lot. If you imagine you have 30 ports, when you do the math, you end up with roughly 500 or even beyond watts, which you just put on the transceiver side, not taking CPU, RAM, and all the other stuff in the switcher router in consideration. So that's a lot you need to provide, and a transceiver is basically taking power and convert it to heat, because the light which we get out there has such a small amount of that power, which is actually not reasonable. So we have to get rid of the heat because we feed in a lot of power, and there are, when you look in today's data sheets of the switches and routers, not every port is supporting up to 17 watts, although the form factor provides it for sure, but the switch needs also to be capable to provide this power to that port, or to amount of port, or to certain ports. So that's very important. And therefore I highlighted the temperature, because you need to focus on it. And if you're running on high temperatures, it's typically like this: you pull more power out of your port than on lower temperatures. And then this is now the tricky part. These are the coherent parameters. This is the current implementation. What we got out of Nokia was end of last year. And I want to go through those different values now, step by step, to show you what are the coherent ones. So the first one I highlighted here, it's the RX channel, and that's new. Previously, DWDM networks, and if you were running tunables in there, you were able to tune the TX wavelength. That applies for coherent transceiver as well, but you also need to configure the receiving wavelength now for a coherent transceiver, because the local oscillator inside of that transceiver needs to lock onto that frequency to get the actual signal out from the carrier. If you don't do it, you can't establish your link. And there is no sweeping, so you can't go through the band and identify the correct channels. So you have to do it manually by your own to say, okay, we are running on channel 23 now, which is the counterpart currently also transmitting on channel 23. And coming now to more optical stuff like the chromatic dispersion. You are familiar with chromatic dispersion when you are running CWDM networks with 10 gig, for example. You might were facing that issue with 1610, 1590 nanometers transceivers on long distance links beyond 40, 50 kilometers. That chromatic dispersion hit in and the link wasn't established, although the power levels were fine. So what is chromatic dispersion in a nutshell? The light is traversing on our fiber, and it's either accelerated or decelerated our signal, and it's going to be changing over time while it's traversing from the transmitter to the receiver. And this dispersion, the chromatic dispersion, can be compensated, and a coherent one can do it. And you see the end and starting point from 2000 picoseconds up to minus 25,000. So the coherent transceiver is capable to compensate this. And down in the middle section, you see the actual chromatic dispersion measured by the transceiver itself. So we have 220 picoseconds per nanometer. And when you know the characteristics of your fiber, for example, a G.652.D fiber, you're running roughly at 10 picoseconds per nanometer per kilometer. And when you do the math, you would end up of a span of roughly 20 kilometers. The actual span was 15 kilometers in this scenario, and we couldn't figure out the offset of 80 picoseconds per nanometer where it was coming from, because our counterpart test was a back-to-back link with 2 meters of jumper cable, and there we ended up with 80 picoseconds per nanometer, and yeah, it was always there. So we had to deduct those 80 picoseconds per nanometer. Beside the chromatic dispersion, as we have two polarized signals now, there's also not only on the signal itself acceleration and deceleration, but also in both polarized directions on both planes. While the light is traversing on the fiber itself, there can be a shift as well. And that's called the different group delay, or called also the polarization mode dispersion. And this is also measured in picoseconds. Here we have 2 picoseconds of a delay between two polarization planes. And the tolerance of that transceiver is roughly up to 10 picoseconds. And you get this out of your data sheet of the transceiver itself to say how tolerant it is, how far we can, having the different group delay there. Moving on, as I introduced the OISNR at the beginning, there's the OISNR in combination with the RxQ margin. The RxQ margin took us a while to figure out, because somehow Nokia started to generating their own words there, because the rest of the industry is calling it the Q factor. So what is the Q factor? It is a combination to the prefec. So we have a FEC inside of the transceiver who is correcting the errors actually, but it can do it only to a certain amount of errors. If the error rate is too high, the FEC can't correct the errors any longer. And the Q margin basically tells us, and shows in dB here, if there is still margin and room for the FEC to operate in the optimal conditions. So here we are running on this 15 kilometer span on 2.4 dB. On a back-to-back link, it's roughly 4 dB margin, which we have for the FEC. And for sure, when the margin is 0 dB, that's the point where the FEC is not capable any longer to reach a certain bit error rate, which is needed for a proper link to work. And the same with the OISNR. The transceiver can measure the OISNR, and this one is running at a really good value at 34.4 dB on both polarizations. In looking also in the spec sheet of the transceiver itself, it can go down to 26 dB of OISNR level, and yeah, beyond that, we end up in a higher bit error rate again. Right. Finally, the Coherent transceivers, they have a really nice feature, and which is called the application modes. The Coherent transceivers are no longer just a single transceiver doing, for example, 400 gigabit. You are able, because there is a DSP inside, to configure it in different ways how it is working. So having just a plain 400 gig transceiver, you can either configure it, for example, in 2 times 200 gigabit or 4 times 100 gig, or even combinations in terms of 3 times 100 gig. And I showed a couple of applications mode, which is just coming out of one single transceiver, basically based on the configuration of the DSP, how it's operated. And I highlighted this application mode number 3. That's now in the industry a well-known application mode, which is defined by the OpenZR Plus MSA. Why do I highlight it? Because the transceiver actually plugged in is not capable to do it. So when you look also on the show port command, we see there is no optical compliance for OpenZR Plus. We're only supporting the OIF, which is a different sourcing agreement of different vendors. the OIF ones are supported now by these transceivers, but not the OpenZR Plus ones. And you see this also on the right side on the line symbol rate. It's a different symbol rate. The OpenZR Plus is running on a higher symbol rate. Right. Why is this important? Maybe I go back to that one again. Is that and when you also do the math of your symbol rate of a line, it's roughly at 60 gigabaud. Doing the math there to ending up at 400 gigabit, because we are running 8 lanes in the transceiver, we end up at roughly 475 gigabit. For Ethernet, we only need 425 gigabit, so there's an overhead of roughly 50 gigabit for the transceiver. Why is this needed? The FEC needs some additional gigabits to operate properly, and within the coherent signals, we also have a pilot sequence, which helps us to correct a phase shift. And this overhead is added that we are able to correct errors at the end of the day. Right, where are we going? The baseline here on this graph I want to show is like a 400 gig signal on 50 gigabaud. When you do PAM4 modulation on it, which is the green dot, you end up with 4 lanes at 400 gigabit, because PAM4 does 2 bits per symbol. Now for the upcoming generations of 800 gig or 1.6 terabit, there are different ways to increase the bandwidth. And in this example, it's very well shown when you change the modulation scheme from PAM4, which we are known from 100 and 400 gig now, and going up to DP16 QAM, which are introduced with the coherent transceivers, you actually can quadruple the speed, so from multiplied by 2 up to multiplied by 8. So we can quadruple the speed actually, just on the modulation scheme, on the change on the modulation scheme. There are other ways as well. When we increase the speed on the electrical lanes, which you see on the x-axis, we are at 50 gigabaud at the moment, but there are ideas and intentions to go towards 100 gigabaud, which is a really fast signal on the electrical side, or even towards 200 gigabaud. And yeah, going up to 1.6 terabit or even to the 3.2 terabit transceivers. Yeah, this brings me to the end of the presentation. I hope I gave you some insights into coherent transceivers. Thank you very much, and I'm open for questions.